the following fact, which is Noether's theorem, that is, given a continuous symmetry, we will get a conserved current. Okay. So, we will write this formula where the only input we have to do is we have to explicitly write out what the symmetry is, and out where you will get a conserved current. Okay. And we will discover that the one which we did a couple of lectures ago for getting the stress tensor or the energy momentum tensor would be an example of that category and the general master formula, and we will keep coming back to the master formula through this course at different points in time. Okay. So, let us sort of recap on symmetry first. So, by now hopefully you are comfortable with the fact that symmetries are best captured by some by the idea of a group. So, when we mean a symmetry, you should immediately think of some group. Okay. So, we already saw that groups fell into two categories, but I will slightly change my definition of them. We will call group either discrete or continuous. Okay. And these are best illustrated through examples rather than looking at the definitions, etc. Discrete is finite groups are a special case of discrete groups. So, for instance, the group Z with plus is it's not, it has infinite number of elements, but it is not a continuous group. Okay, like this, it is not like we have a parameter to change. So, I want to expand the definition of finite groups to include even things like this. Okay. And continuous groups, of course, are SON, we have already seen several examples, SUN, there are many more. The Lorenz group, so on and so forth. Okay. So, these are all continuous groups. So, symmetries also we will classify into these two categories, and the reasoning is just like I mentioned, Noether's theorem actually only refers to, we will get conserved currents only for continuous groups, because here we have a notion of varying some parameter. So, roughly speaking, you think of the identity element which does nothing, and you can talk of a neighborhood of the identity element. So, you have some parameter or parameters which you can take to be small. Okay. And so, there is some notion of a small expanding about some parameter, and that will be very important in what we will in our derivation of this thing. So, these are the two kinds of groups that we will look at, and Noether's theorem tells you that you get only symmetries for this. Okay. And we already seen that just because you have seen a conserved current, it does not necessarily follow that there is a continuous symmetry associated with it. We already saw one current which we call topological, which was in 1 plus 1 dimension, let us call it topological. This was a current which was trivially conserved in 1 plus 1 dimensions, of course, because this is the Levi-Civita in 1 plus 1 dimension. So, this has at least not associated with the symmetry. Okay. We will also distinguish between two kinds of symmetries. Okay. So, types of symmetries we will say. These symmetries that act on space time, okay, and symmetries that do not. Okay. So, such symmetries are actually called internal symmetries. Okay. So, these we have already seen examples of these would be Lorenz transformations, for instance. Also translations in space time. So, these two are examples: parity, time reversal. All these are examples of symmetries that do act on coordinates. By coordinates I mean space and time coordinates. While this will act on field space, so I will give you an example. Okay. So, let us look at an example. Of an internal symmetry. Rather, I will give two examples. One will be discrete and one will be continuous. So, I do not want you to think that I mean certain internal symmetries cannot be discrete or whatever. Okay. So, let us first do the discrete thing. So, let us consider a system with a Lagrangian with one scalar, but this is a simple, this is the one which gave the Klein-Gordon equation. And so, now there is a symmetry which does the following thing. Suppose I take phi goes to minus phi. Does nothing to the coordinates and this thing. Okay. It's very easy to see that this is quadratic in phi's. So, I could even go ahead and add an interaction of this kind, as long as I do not write a cubic or a quintic kind of term, I am okay. So, now this is a Z2. So, this is an example of an internal symmetry, it does not act on this thing. Okay. So, let us do something, make it more interesting. Let us just modify this Lagrangian, where I add okay. So, let us write this way. Let me modify this a bit. No square out here, it is still quadratic if and A is some index which runs from 1 to n. Okay, we are just summing over them. So, there are n species of identical, if you look at identical scalars, and they interact such that this term here is just the quadratic, it is like the length of a vector of some n dimensional vector, Euclidean vector. So, by phi a I just mean okay, and this object is the square of for the square of this thing. So, this remains a symmetry out here, I can still keep it. So, this is a Z2. Okay. So, this is only acting in field space. So, we think of this A index as nothing to do with space time. So, we call this an internal index. Okay. So, now it is very easy to see that there exists a continuous group which acts as rotations in this internal space, n dimensional space. So, there is a new symmetry which says that better to write it like this, and I am really not being particular about upper or lower because it is Euclidean, it does not matter deliberately. Okay. So, phi a prime equal to r a b, but nevertheless I mean repeated index is summed over. Okay. So, where r is nothing to do with space time, it is just some n by n orthogonal, this is some n by n SON matrix. Very easy to see that phi prime A. So, now this implies that phi prime A equal to phi A phi B. Similar way you can see that d mu of phi A also transforms like a vector of SON. So, you have a continuous symmetry which does not act, okay, and of course does nothing to the space time coordinates, only acts in some fictitious internal space. I should not say fictitious because if the it's as real as the field. So, okay. Is this clear? Because lots of people have confusion with this thing. I mean, if you say the word rotation, it has to be rotations in physical space time, not necessary. By rotation here what I mean is SON, the group SON, I mean, and you know that this n could be 1,000,000, nothing wrong, okay. So, okay. So this is an example of an internal symmetry, but the key point here is again this is a continuous symmetry while this is a discrete internal symmetry, and Noether's theorem does not distinguish between whether a symmetry is internal or whether it is acting on the space time coordinates, okay. I do not think this is called external, by the way. So, okay. So hopefully you get the setting of the problem. Here we see that there are, so we have to focus on continuous symmetries to understand this thing, okay. So let me sort of illustrate how the smallness will be used. We will find, I mean, for instance, for orthogonal matrices. So yeah, so let us consider. So, consider SON matrices. Okay, let us call them O, just for, or I called it R out here. So, let me just call it R. So, R, we already discussed this when we were discussing, can be written as the exponential of some antisymmetric n by n matrix, okay, and it's a 1-to-1 correspondence, it's a bijection, okay. And so now I can use the definition of this thing, so on and so forth, okay. So the idea is, what would be the notion of something being small? Small would tell you that it has to be arbitrarily close to the identity, okay. So if you were doing an exponential e power x, okay, you would write it as 1 plus x plus order x square, and this is good when x is small compared to what, to 1, okay. So the same thing holds out here. You will have, so you should think of this as being small, and you neglect this term. So I will just use a similar notation, and but really what you should understand is that this A here will contain a bunch of parameters, and each parameter is taken to be small. So it is not one condition. So let us, I will be more explicit. So I will write here. So similarly I will write, similarly we can write e power a equal to 1 plus a plus order a square, okay. Another way to do this is to introduce some auxiliary parameter which is just a scalar, which we write like this. At the end of the day you can set lambda to be 1. So lambda is like a bookkeeping parameter, and then you would see that I could write it in a slightly nicer fashion. But I do not promise to stick to this notation all the time. I might use the one which I just erased. I will keep going back and forth, but it should be obvious, okay. So let us again come back to this A, and let us choose A to be 3-dimensional. So let us consider the case of maybe I will go to that side of the board. So let us consider the case when n is 3. Okay, so A is an antisymmetric matrix, 3 by 3 matrix. So let us write it out. And this part is just obvious, so I am not going to write it. It is an antisymmetric matrix. So if I specify A12, I write here minus A12, so on and so forth. Okay, so these are obvious. So this has, so when what one means by small a, okay, is the same as saying that both A12, A13 and A23 are small. Okay. So you can see now whenever we talk of things like a square, it will always involve products of these guys, and each one is small or order lambda if you think that way. So if you look at the next term, it will be order lambda square. Okay. But now you can see that out here there are 3 distinct ways of going away from 0, from identity. Okay. Or in terms of this, so the thing is, so this symmetry has, such a symmetry has 3 free parameters. Which are clearly independent of each other. Okay. And in fact, you can think of another nice way of thinking about this is the space of A's forms a linear vector space. Okay. And since we are only doing things to odd, so the space of A's is a linear vector space, which is 3 dimensional. Okay. And in this case it is over reals. So it has 3 free parameters, and so what Noether's theorem tells you is that for every independent parameter you get one conserved current. Okay. So this so Noether's theorem, so it is funny, we are discussing a theorem which we have not proved, but the idea is that I want you to see where we are getting at. Okay. So we should expect one conserved current per free parameter. Okay, by free or independent to be more precise, I should say, per independent parameter. Okay. So one more nice thing about looking at small things is that we will see later is that the structure, the linear vector space structure that I have said emerges in just about all the examples, and this structure is a lot simpler. Adding vectors in a linear vector space is very easy. It is a lot easier than multiplying two two orthogonal matrices. I mean, just proving, if you have to say that e power a1 times e power a2, and I ask you to work out what a3 is, you know that there is a long formula for this thing. Okay. So but what we will see is for many of the things it is enough to understand what happens at this order, and everything rest of it sort of carries over. Okay. So this captures a lot of stuff, and we will see the whole theory of Lie algebras emerge from this simple way of looking at things. Okay. So here we should get, so I should again say this is independent parameters. So we expect, so in this example we expect 3 conserved currents. 3 conserved currents or charges. So it is exactly similar. Again, another example is translations. There was one translation in space, in time, and one for every spatial degree of freedom. So we expect that many currents, and we did get that many currents. Okay. So let us sort of see how this same structure holds for the Lorenz group, because you may think there are, there is a signature change out there. Can we understand that? And what we will see is that again it will have this same structure, and there is a sense in which just as these matrices were orthogonal, However, antisymmetric we will find that there is an analogous thing which will be antisymmetric, but there is an issue of keeping track of indices. So, I will work this out, and it is a good example of why keeping one lower, one upper, etc., makes sense. Okay. So, let us go back, let us look at the definition of the Lorenz transformation, which is just that. So we wrote something like this. So the idea is that we are going to work out the infinitesimal Lorenz transformation. So you will have x prime mu, and this lambda mu nu x mu, okay, where lambda mu nu eta mu rho, lambda transpose which has the opposite structure rho sigma So, this is the definition of a Lorenz transformation. There is of course determinant condition, etc., but what we want to do is we would like to write okay. So, this little bit of Greek this is capital lambda in Greek, and this is lowercase lambda in Greek. Okay. So, I am using the same letter, but the small lambda indicates that it has to do with the exponent, the smaller part, okay, roughly speaking. So, so the thing is like we want to do here, what we want to do is to expand this about identity and keep track only of the first term and ask what are the conditions. If we did the same thing out here, we will see that the condition that this be orthogonal implies that A should be antisymmetric. So, we will work. So, what we will get is the analog of that condition on lambda, and let us see what that is. Okay. So, I just write here 1 plus, so by 1 I mean really delta. Okay. Another thing to remember is that if you have one upper and one lower, it has to be a Kronecker delta. If it is 2 upper, it should be an eta. If it is 2 lower, it has to be an eta again. Okay. Okay, and let me remind you that this lambda out here has not this parameter kind of thing. It is, there are so many of these guys. So, we plug these things in here and we expand it, and we only check okay, the first entry is trivial. When you put a delta, it is trivially true. So, it is really the next one, but what I have to do is to take work only to order to keep these terms, and I am throwing away order lambda square terms. So, for instance, the only way that can happen is this might be a lambda, and then this has to be a delta. Okay. And if I, or the opposite, if this is giving a delta, this has to give a lambda. So, I will have 2 such terms. There is no lambda dependence here. So, this is at 0th order, which is already taken care of. So, at order lambda I only have 2 terms. One is replacing this, and this has to be now a delta rho sigma plus, now the next one has to be delta so this has to be transposed. So, this will be exchanged, these 2 indices. So, this would be a rho, just remembering. Okay. So, we can get rid of these Kronecker deltas easily. So, this just tells you that this rho becomes sigma, and out here this nu becomes mu. So, let me write one formula where I have taken care of that. So, I get lambda mu nu eta nu rho sigma plus okay. I have done nothing so far, but one more thing you can know, I mean I claim that there is no need for me to say this is lambda transpose, because if you look at the index structure, it is exactly with the first index is lower out here and this is upper. So, you can this thing, but it is okay to be, since I am being very pedantic or whatever, I am putting the transpose out here, but I claim that I do not need to do that either. Okay. But let us leave it that way. So, this is what we get, but now we can think of defining so from the special theory of relativity, we know that we think of eta as raising and lowering thing. So, here this what we can think of this, what this is doing out here is to raise this thing up here and replace making it a sigma. So, that is the definition if you wish, okay. And I should keep track of where this raised index goes. It is the second index. So, this term I will write as lambda mu sigma, okay. And what is happening out here, the same thing is happening, okay. And but now it is raising the first index. So, this should go up here, okay. And now I will do what I said, I will get rid of the t, I will not show that it is obvious, I claim it is done, I mean it is already taken care of, then you get. So, what this does is it raises this row and makes it a mu. So, I get this thing, okay. So, you see that yeah, when I wrote, the minute I wrote lambda transpose, I did exchange. So, yeah.
How does it give lambda sigma mu? The row is on the left or the sigma is on the left?
Which one?
On lambda transpose.
On this lambda transpose, the first index is a lower index,
okay,
and the second index is upper. That is all, as opposed to here.
And when you are contracting with eta mu row?
Which one? So, it has to be acting correctly, right?
The next step.
The next step, yeah.
No, the one below it.
Yeah, below this, yes. So, this mu is raising this guy, but it will not change any position or anything, it just makes it go up and makes it a mu.
That will give a
mu sigma.
But no, but that won't
no,
make
no.
sense. So, when you are getting into a transpose, should we?
No, wait, yeah. So, wait, let me write this. So, let us do this. So, let us write whatever we get, mu sigma. Are we okay now? Okay. Yeah. So, if you want to get rid of this, I have to, yeah, you are right. So, this tells you that mu sigma plus lambda sigma mu. Now, I have got rid of the transpose. So, that implies that this is antisymmetric when you raise the indices, okay. And but thinking about I mean there is no way of saying that something which has this kind of dissimilar index structure, one covariant and one contravariant, they can't come. I mean antisymmetry is comparing, you exchange two identical objects and you get a sign, that is what it says. But as it stands here, there is no way for you to exchange it. So, intuitively what this says is you need an eta to raise it, okay, and that is what is antisymmetric. In fact, if you just went ahead and looked at let us take a simple example of the boost matrix in 1 plus 1 dimension. So, the phi here, the rapidity is the analog of these a's out here, that is small. If you take this to be small, okay, so this would be some lambda, this matrix with one upper one lower. If you expand this for small, it is 1 1, but then the order phi term so now you naively think fine, this looks like a symmetric matrix, but transposition does not make sense out here, okay, because this formally if you look at a matrix, it does not, you can't, I mean this as it is written you can do a transpose and it looks like it is a symmetric thing, but actually that has no meaning. If you keep track of the index structure, what has meaning is only after you raise it, and a nice exercise is to raise this and you will see one of these pick up. In one case you will be raising a 0 index, in the other case you will be raising one spatial index. So, one of them anyway has all you care about is a relative minus sign. So, it is independent of signature if you wish. So, this will become an antisymmetric matrix. So, what is antisymmetric is the thing which like indices. I could have equally well have written lowered both of them, even that will hold, okay, or this is also true. okay, both of them will be true. Is this clear? Another warning is with for instance, if you have something like T mu nu and you are asked to take the trace of it, okay. Can you tell me what is the trace of T mu nu? What would you do if I asked you to trace T mu nu? So just say whatever, I mean there is nothing about right or wrong, we will see. How about you? What? Exactly. So the natural thing you would have in mind is take the sum of the diagonal elements, but that is not correct. The reason being that would say that you want to trace sum over both these two elements mu mu, you would think, but T mu mu does not make sense. Okay, so the way to do this is to write it like this. You contract with a T eta, which is a natural metric in this space, and this will tell you. So this will, if you look at this and expand it out, you will see that this will tell you that what you are summing over is T 0 0 minus okay, or another way of saying this is what I do out here is to raise the second index up and then I sum. This is what we should sum over. These are all related to the same thing, but you can see that if you were in Euclidean space where eta is the metric is just the Kronecker delta, then it is exactly what you said, it is just the sum of all the terms. Okay, so now if you are in some weird curved space, then the trace would be done by whatever is the metric in that space. It won't be even so simple. Okay, so just remember that this is a subtle thing, but it is an important issue. Okay, and this is the, see, the key point is what you want is you want this object to be a Lorentz scalar, and this is what when you trace it, it is a Lorentz scalar. Is that clear? Okay. So let us now start the process of getting towards proving Noether's theorem. No, not necessarily, because I could for instance take another example. I could have something else like this, T mu nu rho, which is a third rank tensor. So then you have to tell me when you say trace over which two indices, you have to pick a pair. Okay, and when you trace here, the answer here would not be a scalar like here, but it would be a vector or a covector, in this case a covector, because it is any pair, yeah. But if you, I mean, you can trace over pairs of indices and stuff like that, I mean that is perfectly possible. So I mean I just chose the simplest, and this is an example, this is something which will come in this course. So I am just warning you, because this is a common mistake people make. Okay, so we want to prove Noether's theorem. So now we got the machinery going, so we will not assume we will write out the most general thing. So let's say that the symmetry acts on both space time as well as the field space. So delta x mu equal to, or let us write it this way, x prime mu is x mu plus a mu of x. Okay, this is not a translation like we did earlier, it could be x dependent. For instance, under Lorenz transformations you will see that it is linear in x. Okay, and so let's keep a bookkeeping device now. And let it act on the field space as well. We do not know how it acts. So just for concreteness, I just put some index a out here, and just R is no longer a rotation matrix or anything, it is just some matrix, it acts not only on space time, it also acts on things like this. Okay. So, now what I will do is, again I want to assume that this is equal, this is I want to write it in this fashion. So, it will be some phi a plus some bunch of parameters. So, let us just call it okay, that is this free parameter. I am just thinking, I am just thinking I am looking for some parameter which will not okay, yuck. Okay. Okay, plus order lambda square. Okay. So, I am telling you how it acts on field space. So, at the end of this there will be some parameters which I so these will be well defined functions. So, let us just consider let us look at the two examples which we already seen. So, let us do first example one is internal symmetry which is SON. Okay. So, in such cases for this example a mu would be 0, it does not act on it, but it does act on this alpha a b would be those parameters which I wrote. So, we will actually let me leave it this way, alpha a b will be the 3 or n into n minus 1 by 2 parameters. So, if it is n equal to 3 for instance, I can be more explicit, I would write phi prime 1 equals to phi 1 plus a 1 2 phi 2 plus a 1 3 phi 3, phi prime 2 would be equal to minus a 1 2 phi 1 plus phi 2 plus a 2 3 phi 3, and similarly of course plus. So, this should all have a lambda going with it. So, that is a bookkeeping device. Any more lambdas? Okay. So, is this clear? So, this alpha a b will track all these. So, in this case this would be these guys. Okay. Now, let us do the same thing for okay. So, let us do for Lorenz transformation. So, this is example, what did I call it, example 1, example 2. So, what should I write here? Okay. So, this is what I called there. Okay. Actually, it is important to realize that even if the parameter lambda is small, this combination a mu need not be really small. Okay. Think about a rotation. I make a rotation by a very small angle, but if you ask how much distance it moves, it is like if you go to a distance r away, it changes by r times the angle. Okay. Theta could be small, but I could make r arbitrarily large. Okay. So, there is a formal sense in which this aim. So, that is one reason to think of this lambda parameter which I am writing out here as a bookkeeping device as a formal parameter. Okay. So, I am not really I mean I would be wrong in assuming that mu is small, even though lambda is. Okay. It depends on the x's which go. Okay. What about, let us say we have a single scalar field. For a single scalar field, we know that we get something like this: phi prime of x prime should be equal to phi of x. If it had, even if they had the indices, it does not act on the indices at all. The Lorenz transformation, if it is a scalar field, this is for okay. But if you have a vector field like a mu, this should be equal. Now, I will have two actions, one coming from the fact that this index is a vector index and the Lorenz transformations do act on that. So, I would write something like this: lambda mu nu okay. It is not yet in the form which I have written out there, I have to massage things a bit. So, we will do that for both of these cases. Is this clear what I have written? So, here A is just for some n scalar fields, each one of them is a scalar field. This A is some internal index. So, rotations do not have anything to do with them, rotations or boosts or whatever. Okay. So, this is what happens. So, now let us work out what. So, what we want to do is to rewrite it in terms of the small parameter, which is in this case lambda mu nu. Okay. So, we just go ahead, plug things. So, what we get from for the first, for this we get, we can write x prime as is x plus a mu. Okay. This should be equal to phi of x. Is that clear? Okay. So, now if we expand things, so what we get is so, I have just expanded this to first order in A, okay, but really first order in that formal parameter. Okay. So, now we can even rewrite this yeah. So, we can rewrite this as or now you may worry, you know, this is with what is the derivative with respect to or whatever x prime, but really it is not a big deal because it is an order a square thing. Okay. So, all I do is when I take this to the other side, I put a minus sign and then you just say that everything here is with respect to the x variables, not the x prime, but anyway there is no x anymore. That is for okay. So, now we have finally written it in that form. Okay. And what is a mu? A mu is defined already here. Okay. So, let us work out what happens for this thing. So, now you see here there are extra pieces coming, there is one piece coming from here. So, we can, so there will be, so let us write that a mu prime of x plus a equal to 1 plus lambda mu nu into it should not be 1, it should be okay. Now, again I expand this, So, I cannot use the index mu as my dummy index because it is a free index. Should I be careful here? Should I have written a transpose? Yes. Okay. Just remember, because I mean I am using a covariant guy, so I should write the transpose. Okay. So, lambda transpose mu nu nu. Okay. So, now again I can rewrite this by taking it to the other side. First term of course is, then you get one term like this. Okay. And okay, let me rewrite this here so that you can see it and compare them. Okay. And just to make the match more perfect, let me replace the dummy index. Okay. So, now you see that this term is common to both, but the fact that this is a vector field actually gives you an extra piece. Okay. So, what I called alpha out here, okay, is something more complicated than this, but you can see that it roughly fits into that thing. So, alpha there in this example is delta AB, but there is more to this story. Okay. There I just said that I keep track of the various, this only is what it was doing on the internal index space. So, the alpha is just a delta AB, okay. But there is this piece, because I mean I have not written that out, I hid that in what I wrote, but we do, I mean now that I put everything in, you can see that this is what you get, and there are extra pieces, because this field has an index which transforms non trivially under the Lorenz group. Okay. Is this clear? Okay. So, if you give any symmetry, the first step is to say how does it act, and since it is a continuous group, you have a notion of what you mean by infinitesimal, go ahead and do that. Okay. So, the idea here is that so one thing we know is that given a symmetry, the action will be invariant under that. So, what you mean is that so the action in terms of, let us stick to 4 only, which is d4 x prime L of I will write it only for scale, I mean I will just use a notation phi a, but I do not think it should be hard for you to replace phi a with a mu. Okay. So, and their derivatives, everything will be with the primes. No more primes here. So, this is just a statement that the action is invariant. Okay. And one new ingredient which comes here is because if you when things act on space time, then there could be a non trivial change in the Jacobian between x prime and this thing. So, we need to work out, so we need to include the Jacobian in going from x prime say d4 x prime to d4 x. Okay. but life is easy because we do not want the exact expression for the Jacobian, we are going to work always to first order, and we will see that there is a very very simple formula which you can write for the Jacobian without any problems. Okay. So, we will have to include this, but another thing is, if you may wonder why we did not even look at the action when we discussed the energy momentum tensor. The reason is there that this A was a constant and there is no Jacobian. The Jacobian is rather the Jacobian is 1. Okay. So, that is why we did not. So, but in general, I mean, in fact somebody, I think Albin had raised the issue that about the measure, and I said for this the measure is 1, but he was right, we need to start with the full action, okay, which I did not do, just to simplify things. Okay. Yeah.